Oh hey guys, don't mind me, I'm just playing with some toys in electrostatics or doing voodoo magic, one or the other, not sure which. This is the review video for AP Physics about electrostatic forces, electrostatic fields, and also electric potential. If you're not in AP Physics, you might still find this useful, but you might need to know a few things first. If you are in my AP Physics class, hey guys, hope you're enjoying your Senior Service project, and check this video out so that you can do your homework and so that you come back up to speed. All right, to begin, some formulas that ought to be familiar. An electric field is given by KQ over R squared, R hat. If you recall, R hat is this business here with components. All right. Furthermore, the force on a charge little q in the field produced by a charge big Q is given by F equals QE. So if you put the two together, you end up with the force is this. Or in general, force on a little charge in any kind of an electric field is given by F equals QE. So really, this right here is the preferred equation that you would use to calculate force anytime they ask you to calculate force. All right, the constant K is 9 times 10 to the 9th, roughly. Your textbook might use 8.99 times 10 to the 9th. Usually I'm not particularly concerned about the units, so that's why I didn't write them here. But if you did care about what the units were, since force has to come out to newtons, and this is measured in meters, and these are each measured in coulombs, that means that the units for Coulomb's constant are newtons, meters squared per coulomb squared. That way the meters cancel out, the coulombs cancel out, and you're just left with newtons. All right, I guess one more reminder about units here. Since F equals QE, the unit for an electric field is going to be newtons per coulomb, since force is newtons and Q is measured in coulombs. There's another unit that we're going to see for electric fields when we start looking at electric potential for review, but that's a good starting point for what we're going to look at right now. Okay, I wanted to do an example question here with this setup here. So if hopefully this displays okay on the internet, but we've got a plus Q up here, plus Q down there, a minus Q over here. This distance I'm calling root 3D. What is D? Well, this distance is D. I don't know what D is exactly, but it doesn't matter. This is a symbolic problem. Okay, so root 3, also root 3. Okay, and then over here is just a point in space where I'm going to ask you to find an electric field later on in the problem, and that is a distance D away from, I guess the origin is right there in the middle. Okay, so let's take a look at it. Anytime they ask you to calculate something like the net force, which is what I will ask in both of these right here, there's kind of two possibilities or two approaches. One is if it's all point charges, you can just go straight to this equation right here and do your multiplication and your vector addition and all that kind of thing. The other possibility is perhaps you already found an electric field at some point, and now they want you to calculate force on a charge that's placed there. You could do that using then F equals QE. So if you already know the electric field, it's a simple operation to multiply the charge in that field times the magnitude of the electric field to arrive at force. It would be way more complicated to start the whole question over again. So don't do that. If you already know the field, you would go straight to F equals QE and just multiply by a little q. All right, so we're going to try and find the net force on, in part A, the top positive charge. Okay, all right, so this will be fun, or something. All right, so we said this is the formula for force between two charges. The R hat, remember, has to do with components, so we're going to have to worry about components. the starting point for any question having to do with either electric forces or electric fields is going to be draw some vector arrows on your diagram. Okay? So the positive charge is going to be repelled away from the other positive. So I'm going to put the force on it due to the other positive is going to be that way. All right? That's plus plus to indicate that it's the force from the other positive charge. All right. The minus charge is going to attract it. So that force would be that way. Okay. And now if I want to add these two forces together, I've got to get a magnitude for each one, and I've got to get the components for each one. All right. Let's start with plus plus because that's the easiest one to work with. The equation for force is K Q Q over R squared R hat. Both Q's are the same magnitude. For this equation, all you ever actually plug in is magnitude. That's it. You don't worry about whether it's a positive or a negative charge. That's the sort of thing you would do when you calculate electric potential. But as far as signs go, for forces, signs correspond to direction. So don't plug in like a plus or a minus sign here. Where you would plug in a plus or a minus sign is when you start worrying about the components for things. So, for example, when I do the force between the plus and the minus charge, that force is going to have a positive I component and a negative J component, not because this is a negative charge, but because that's the direction that it goes in. Okay, so this one here. Both of the Q's are the same magnitude. The distance between them is root 3d plus another root 3d. So that's 2 root 3d. That's going to get squared. Oops, got my r hat. For this one, the r hat is really not going to be especially important, as you may have already realized. When I square 2 root 3, that's going to come out to 4 times 3 is 12, so 12d squared. So k q squared over 12d squared. All right, and then r hat. R hat is this thing here having to do with components. When we get to the force between the plus and the minus, it's going to be more involved. And it's going to involve things like looking at, say, the fact that cosine is adjacent over hypotenuse, and sine is opposite over hypotenuse. But for the force between the two positives, it's all directly in the j direction. You don't need to mess around with components. You can just go ahead and say it's 0i and 1j. All of it is in the j direction. So I'll just go ahead and put j. All right, so if you're looking back at this and thinking, wait, how did the r hat become a j hat? It became j hat because that particular force is perfectly upwards. There's no left or right to it, so we don't need to worry about cosine or sine. It's 100% in the j direction. All right, so that's the force between the two positives. The force between the plus and the minus is going to look a little bit different. Same formula. All right, to begin with, the distance. I, on purpose, picked some distances that would be a reference triangle so that I wouldn't have to mess around too much with Pythagorean theorem, but that distance there, if you're familiar with your 30, 60, 90 triangles, ought to be 2d. Okay, so that's 2d right there. Right, so if I square 2d, I'm going to get 4d squared. All right, so there's that. And then for this one, I actually need to go through and do the r. All right, so for that one, the for this, let's worry about sines first. For the sines, you've got to think about, all right, is it plus I or minus I? Well, that's clearly to the right. That's going to be a positive I component. Next, where should I pick an angle from? Well, it doesn't necessarily matter where you pick the angle from. Oh, I'm sorry. I labeled 2D down there, and I should have labeled it up here. My bad. This distance is the same, though, because I made it be very symmetrical. All right, fine. So when we say it's cosine theta I and sine theta j, that's assuming that you pick an angle from the horizontal. If you didn't pick an angle from the horizontal, it wouldn't work out that way. Now, if you did pick an angle from the horizontal, then it would work out exactly that way, and you'd be all good with it. And that's what I'm going to do here. I'm going to say there's theta. All right, so if I do that, then the adjacent side here is d, and the hypotenuse is 2d. So that means that cosine theta would be 1/2, because d over 2d, the d's will cancel, and you just get 1/2. So I'll have 1/2 I. All right, now let's do the j. For the j component, that one is down, which is in the opposite direction of the other one. By convention, down is usually a negative. So it's going to be minus whatever it is. All right, what is it then? The opposite side to the angle is root 3d, and the hypotenuse is 2d. All right, so sine of theta is going to be root 3 over 2. In this case, you might be thinking to yourself, well, now, Mr. Erico, couldn't I have just said that's a 60-degree angle, and cosine 60 is 1/2, and sine of 60 is root 3 over 2? Am I right? Yes, you could have, but the thing is you don't always know what the angles are. They don't always tell you an angle, nor do they always give you a reference triangle where you can just say, and here's the angle. Instead, it's usually better to take it as it is and just say sine of whatever theta is, and I don't care what it is opposite over hypotenuse. And then you find the opposite side, find the hypotenuse, and plug those into opposite over hypotenuse. That's usually the better way to do it. All right, so then root 3 over 2, j. There it is. Okay. Now I just got to combine my like terms and stuff. That would be a little bit annoying in this case, just because of what I've got, right? This is a j. This is a j over here, and it's not necessarily going to combine nicely. So I'm not going to worry about simplifying it. But yes, your j's would combine together, so you'd have I, and then something more complicated looking j. Okay, that's going to work for the total force on the positive charge. I'm going to just kind of flash forward to the answer for the net force on the minus charge. And then you can feel free to pause the video and look at the work and see how that's going to go. And magically, there we are. There are the two force vectors. This one, oh, sorry, I have those going in the wrong direction. Oh, my magic video pause didn't work correctly. Attracted, attracted. There we go. All right. You've got the j components are going to cancel for those two force vectors. There are two such force vectors. Each one is going to have a magnitude of kq squared over 2d squared. And since we're only keeping the I component, I'm going to multiply by 1/2. Really, it should be negative 1/2 because those two forces both are to the left, roughly speaking. All right? So then the net force is just going to be this right here. And if it's as simple as that, where you can say those components cancel, then you don't even need to write them. All right, there's going to be a part 2 video now where we're going to work with forces using F equals QE.